Let us consider the Lagrange interpolation formula. I am looking at higher order derivatives, right. So we use the Lagrange interpolating polynomial to find out the intermediate values in the last class. Now I quickly went on to getting the first derivative, second derivative, and then I went to Laplace equation. I did so many things very fast, okay. So now I will try to slow down and let us go through the whole thing again. So the phi is given by okay. So far so good. So the beauty of this is at exactly x0 x1 and x2, at x0 x1 and x2 this will be exactly satisfied, there will be no error, but it does not mean that at all intermediate points it will satisfy, because using 3 points we are approximating it by a quadratic. So there will be error when you interpolate between these things, interpolating in between x0 and x1 or x1 and x2. But given that you have only 3 points and you want to have a polynomial which passes through all the points, the best is the polynomial of order 2, this is the best you could get. Locally you can have a linear interpolation between x0 and x1 and x1 and x2, this is what you did in your using stream tables. But if the function is non-linear, okay, this is a much better approximation compared to linear interpolation, though linear interpolation can be quickly done on your calculator, right. This will take a little longer time, but this will be more accurate. I also told you that it has wider ramifications, you can take the derivative at dt by dx at x equal to 0 multiply by k and use the energy balance equation, get the heat transfer coefficient, skin friction coefficient and so on. Now let us try to get d phi by dx this will be is it correct? Yes. No, let's first get the general expression. Any problem? Okay. Now what will this become? Huh? Can you simplify? Not 2 pi, that is d squared, or you want to take d squared, go ahead, no problem. Let us take the okay. If that is you have got a equal spacing or equispaced, we call them as equispaced intervals, then d squared phi by dx squared. It is the same everywhere. Sendil, you had a doubt, d squared phi by dx squared is the same whether it is evaluated x0, x1 and x2, because we are having only a second order polynomial, correct. So d squared phi by dx squared two by
delta x square.
2 delta x square, correct. Minus by delta x square plus okay, is actually equal to is that correct? This is purely from getting an interpolating polynomial. By using the concept of an interpolating polynomial, using a second order accurate interpolating polynomial, we are able to get the second derivative of a variable phi. That variable phi could be anything, it could be temperature, it could be stream function, it could be potential difference, whatever, depending upon whether you are a electrical engineer or a civil engineer or groundwater potential. There are so many, phi can take on any value, phi can assume any form, right. Now, so this basically is called the central difference approximation in finite difference. Okay, what is the central difference approximation? Okay, what do you want to call it as? Similarity to or so the central difference is basically one way of giving a discrete form for derivatives and so on. So it comes under general concept of finite difference method. So in finite difference method, where you do is what you do is basically use a Taylor series approximation. Okay, what is the connection here? Okay, so this x naught okay, so we can draw something like this. Okay, now I can actually replace it by to be consistent with the terminology used in finite differences. In a one dimensional representation, this will be xi, okay, right. So this will be phi I. In a two dimensional representation, this will become phi I j, okay, where j is along the y direction. So this is x direction. Now I can say that at xi I am assuming that this is delta x, this is also delta x. Okay, it is perfectly okay for me to say that the d squared phi by dx squared at this point will be equal to d phi by dx ahead minus d phi by dx behind divided by the same delta x. I have taken this to be the bisection of these two, this to be at the bisection of these two. Therefore, when this is delta x and this is delta x, this is also delta x. What is the finite difference representation for d phi by dx? Therefore, this is the way central difference is worked out in when somebody teaches you finite difference methods. Okay, now you can see that the result you obtain using finite difference is very similar to what you obtain using Lagrange's interpolating polynomial. Is that clear? This was not very clear in the last class, now it should have become very clear to you. Now I can use a Lagrange polynomial of order 3 and 4. So this equivalently in finite difference, this will lead to what is known as higher order schemes. Mathematicians are always constantly trying to develop higher order schemes in order to improve the accuracy, convergence of various types of partial differential equations. Engineers, we want to get a quick solution, we want to get an engineering solution, a solution that works, with which we can design ships, airplanes and so on. Mathematicians are always interested in convergence, existence, uniqueness. They want to clean up the mess left by engineers. Okay, we do something and then we don't any engineer will ask what is the order of the scheme, what is the order of the error and all that, what is the order of accuracy, we say no it works, I have done grid independence, that is all. But those fellows want to clean up. Suppose you have a Taylor series expansion, they will take the untruncated series minus truncated series, what is the order of the error, how it proceeds with iteration. So they will, so what they want is paper, pencil and dustbin. No, even now today if you go to TAFR, for example you visit TAFR either in Bangalore or Bombay, so there is a group of professors on partial differential. I have talked to many of morning they will come, they don't have lectures also, they don't have BTechs or this thing, they teach one course a year or something. They will take their paper and pencil, they will keep on solving some partial differential equation, they will try to integrate it, this thing, and they will try to find error in this thing, and so they will say that we are cleaning up whatever the engineers have left. Okay, so that is what they try to do, higher order schemes and all that. So in this class I have simply demonstrated, I have just given a simple demonstration that the Lagrange interpolation formula, if you get the second order, if the second derivative it is the same as what you would have got using a Taylor series approximation with central difference. Okay, so what is this? This is called the forward difference. This is the backward difference, right? We can also write it as phi east minus 2 times phi correct, where this is phi of p phi or phi whatever. Okay. Now consider so right, I am teaching simulation for you, how to simulate 2D steady state conduction. You can simulate it using, I mean you can get it analytically, you can go to MATLAB or you can use Fluent and do it. But of course this is not system simulation because there is only one system, but if when you are considering a coupled system, when you are considering several systems in series or parallel, then it becomes a system simulation. For example, let us take a slab like this. Okay, so this is x, this is y. Let us say it is maintained at 100 degrees centigrade. Okay, so let us say constant k no heat generation, steady and constant properties. So, the governing equation is del square T is equal to 0, correct? That is this is called the Laplace equation, okay. Del square is called the Laplacian operator. You can solve it by using the method of separation of variables, okay. You can solve it using the method of separation of variables. How do you do that? Assume that temperature is assume that okay T is a function of x y. Now I assume that this is a function of x into, that is I assume it to be a product of two solutions x of x into y of y, where x is just a function of x and y is just a function of y. When I substitute this partial differential equation is broken down into two ordinary differential equations. So the left hand side will be a function of x, the right hand side will be a function of y. There is no reason when the left hand side is a function of y and the right hand side is a function of x or whatever, why they should be a function of x or y either. They have to be equal to a constant. If that constant is proposed as lambda squared or something, then you will get two ordinary differential equations. If you solve, you will get separately the solutions for x and y, and then using the boundary conditions you can get all the constants a, b, c, d. This is how you close the problem. Now you have to see what are the possible forms for x and y for this problem. In this case you can see that since the left side is 0 degree centigrade and right side is 0 degree centigrade, the temperature is expected to be symmetric about x. So you will have a sinusoidal variation in x. So you can choose a sine form for x, whereas the temperature is decreasing monotonically from 100 degrees to 0 degrees along y. So the temperature will go like this. So you can have, so you will have e to the power of minus, or you can have e to the power of is also similar to sin h ml and cos h ml. This is what you got in your Finn equation also. The Finn temperature distribution exponential is very similar to hyperbolic function. So you get a composite function where one is a sinusoidal and one is exponential if you combine. So this is what is called an elliptic equation, because information on all the four boundaries is required to solve this problem. So 100 degrees 0 0 0, I have got 4 boundary conditions. So it is second order in x, it supports 2 boundary conditions. It's second order in y, it supports 2 boundary conditions. If I use all the boundary conditions, I can get a, b, c, d and solve the problem. Fine. Now how do you solve it using finite differences? If you want to solve it using finite differences, we already have a representation for this. Okay, this is for d squared phi by dx squared. Now I can call it as dou squared phi by dou x squared, where phi is the temperature in question. Similarly, you can write out an expression for dou squared phi by dou y squared, and then you will get a expression relating the temperature at a particular node in consideration in relation to the neighboring in relation to the temperature at its surrounding nodes. You will get a relationship for every such node, every such phi of p. Then if you so you get a set of simultaneous equations. Go ahead use the Gauss-Seidel method and simultaneously solve. That is the story. Okay, so this is basically 2D steady conduction. So it's called the principle of superposition. It's valid only for linear partial differential equations. It cannot be done for the Navier-Stokes equation, which is non-linear, right? Okay, consider the same problem. Okay, so now, this is phi of p. Now delta x equal to delta y, assume. Okay, so d squared phi is the temperature, for example. So for this, using this, you can write that Please note that I am writing again delta x square because delta x equal to delta y equal to 0. So if you simplify, it is as simple as that. So the value of the temperature at a particular node is the algebraic average of the temperature at its surrounding nodes. Looks reasonable, provided delta x is equal to delta y. So this is also the commonsensical answer you would have obtained, right? So for the problem under question, if this is the problem I had given you 100 0 0 0, if the whole thing were considered to be, if this is considered to be delta x for example, then this temperature will be 100 plus 0 plus 0 plus 0 by 4, it will be 25 degrees centigrade. Whatever sophisticated mathematical technique you use, the center temperature must be 25 degrees centigrade, it will be equal to 25 degrees centigrade. So this is the first exercise I give to students doing project with me, either BTech, MTech, MS or up to PhD. I will ask them to write a code and then keep on changing the number of elements, okay, keep on changing delta x, delta y. You can use a 4 by 4 grid, 7 by 7, 9 by 9 by 9, 11 by 11, use a central difference approximation, use uniform grid, non-uniform grid and prove that the center temperature is very close to 25. Once you get results where the center temperature is close to 25, then your results are insensitive to the grid and they are also validated because there is an analytical solution which is possible. This is a trivial problem for which an analytical solution is possible. In those cases where an analytical solution is not possible, you have to turn around, go back to literature and find out how other people have done experiments and got the solution. So if your numerical solution agrees with those experimental results, then you have a scheme which is grid independent, which is also validated. Now you will say that these are certain features which I have masked in order that I compare my numerical procedure with those experiments. Now in these experiments these features have not been considered, I will turn all these features on and I will get new physics, and since my solution is already validated and grid independent, there is no reason why the solution should misbehave if I turn on the additional features. This is research. Find out what other people have done, okay. First find out what other people have done, find out some mistakes or some critical gaps which they have not filled. So once your literature survey is thorough, get armed with your arsenal, ammunition and weapons, you learn numerical techniques or you do experiments, okay. Then when you are doing numerical analysis, you do go through all this grid independence, validation, write your own code, use MATLAB, use Fluent, whatever, and once you are clean, then you start doing your parametric study. You obtain Nusselt number as a function of Reynolds number, Prandtl number, whatever, and then using your knowledge of regression, get a correlation for Nusselt number and say that it can be used in this situation, it is of engineering significance. Try your luck, along with your guide, write a paper and send it to a journal and see how far this flies. Research is so simple. But you should come and work, that is the thing. Okay, so is this clear now? So we got this east, west, north, south divided by 4. Suppose there is heat generation in this, what happens? Correct? This you must have learnt in your heat transfer course. What is this equation known as? Laplace. Poisson equation. So what will happen is, look at this, these two terms will give phi east plus west plus north plus south minus 4 times, correct, minus 4 times phi of p divided by, if you have delta x equal to delta y, divided by delta x square plus qv by k equal to 0. Then you can rewrite this in terms of phi of p, and then you will have an additional term which is a consequence of this. Why does this term arise? For example, if there is a nuclear fuel rod, okay, so it is generating, there is a nuclear fission which is taking place here, the heat is taken away by the sodium, For argument's sake we assume that there is a temperature, the heat transfer coefficient is so high so that the T S must be equal to T infinity. Now the temperature distribution will be like this. For this the governing equation will be d square T by dx squared plus QE by K is equal to 0, because you assume that the temperature is a function only of x, temperature is not a function of y, because it is infinite in the other direction. If this were to be a slab, this heat generation could be either because of the chemical reaction or a nuclear reaction and so on, so you will get the Poisson equation. You can still apply the Lagrange interpolation formula and finally relate the value of the node at point P to its neighbors east, west, north, south divided by 4 plus QV by K, and you can develop a numerical scheme and use the Gauss-Seidel method. And because if you have 1 2 3 4, so suppose it is simple without this, which we call it as a plain vanilla problem, for example Q is equal to 0, then you know that this fellow will be this plus this plus this plus this divided by 4, this fellow will be this plus this plus this plus this divided by 4, this fellow will be this divided by 4, and boundary conditions are given. So to start you will say T1 equal to T2 equal to T3 equal to T4 is 20 degrees, 30 degrees, 40 degrees to start with, and then it will eventually converge, because it will be diagonally dominant and all that, all those features will be there, because you are always getting that 4, east plus west plus north plus south minus 4 times P divided by 4. So it is at least equal to the sum of all the coefficients. Are you getting the point? Aii is equal to sigma of Aij for all j not equal to I. All right, fine. So with this we close our discussion on Lagrangian interpolation formula, right. So if I keep on developing this, so this will become a course on numerical analysis or numerical analysis of PDEs. We just start with ODEs, PDEs, and we can keep on solving various problems. Of course, if it gets tricky when there is a fluid motion, then it will become Navier-Stokes equation, then pressure comes, then if it is compressible you need to have the equation of the state, then you need to know whether it is transonic, subsonic, supersonic, hypersonic and so on, then it becomes more and more messy. Shock waves will be there, okay, for supersonic, then supersonic combustion you have to solve Navier-Stokes equation, equation of energy, species concentration equation. Where are all these used? Suppose you want to fly a aircraft Mach number 6.5, not aircraft, a missile. Why do you want to do that? 6.5 Mach number, what do you get? What is a great thing? Even supersonic flights we have discontinued, right? Concorde. Why you want to do Mach number 6.5?
Cannot be intercepted.
Simply you want this. So we have 20-second flight, this thing, and we have a nuclear warhead attached to it, and if you demonstrate supersonic combustion, hypersonic combustion Mach 6.5, so it will be released at an altitude of 32 kilometers, and then you fire. So this will be and then kerosene will be the fuel, kerosene will be the fuel, and so even if it flies only for a few minutes, it's enough. This technology is not demonstrated. NASA has demonstrated it for up to 20 seconds or 10 seconds. India is doing that for 20 seconds. 20-second flight we are doing. It's called HSTDV. Okay, hypersonic technology demonstration vehicle. It's being developed in Hyderabad. Okay, so now Newton's yet another way to, please remember that we are still doing exact fits. We have 3 points, we are trying to fit a polynomial which goes through all the points. So you can have what? No. Okay, so this is called the Newton's divided differences method. Here the x0, x1, x2 all need not be equispaced. Okay, so substitute x equal to x0, what do you get? Y0 equal to a0. So you get, what do you get? If you substitute x equal to x0, everything will become 0 except the first term. So the y0 itself will become, y0 will become, what is the problem with this? We are trying to fit a polynomial for y in terms of x. Okay, so we have to get all these coefficients a0, a1, a2. Now I am giving you the procedure to determine all these coefficients. So if you substitute x equal to x0, then all the things will vanish except the first term. So you will get a0. Now substitute for x equal to x1. So y will be equal to a0 plus x1 minus x0. Correct, all the other terms will vanish. You already know a0, you know this x1 minus x0, so you will get a1. So get all a's. What's the big deal? Why can't I have a polynomial y is equal to a0 plus a1 x square plus a2 x2 square a3 x3 cube and all that, and get 4, suppose it is cubic, have 4 equations, 4 unknowns, and solve the 4 by 4. Here all the coefficients are determined sequentially and not simultaneously. So there is no need to solve a set of simultaneous equations. It is a lot simpler compared to the polynomial. Even Lagrange is a lot simpler compared to the first polynomial which we did, because the coefficients need not have to be simultaneously determined. So if that is a pain for you, then go for this, solving it simultaneously. If you have a solver, if you have a library, see we have some IMSL, right? We have some IMSL library, subroutines and all that. If you can take the Gauss Seidel or Gauss Jordan or Gaussian elimination, you can straight away do it. Otherwise, you do this sequentially. Okay. So the last technique which I want to teach you is a spline approximation. Suppose if this f of x was x, okay, I will join it by a smooth curve. What did I do now? It is a smooth curve, right? How obtained? The key is fit lower order polynomials for subsets of the points and mix and match all of them to get a nice smooth curve. But all the curves do not follow one equation. Locally every 3 points are having a parabola, or locally every 4 points are having a cubic. But then in order to avoid discontinuities at the intermediate points, you match the functions as well as the slopes. Okay. So you will get again a set of simultaneous equations, and if you solve for all this simultaneously, you will get the various values and of the coefficients, and this is how spline fitting is done. Okay. So fit okay. can you start subdividing this interval and then identifying how many polynomials are required? Can you start this if we were to do quadratic spline for this? Can you do this? In the meantime I will take attendance. Okay, so this interval 1, interval 2, okay. So here it is a1 x square plus b1 x plus c1. So here it is a2 x square plus b2 x plus c2. Here it is a3 x squared plus b3 x plus c3. We have only the value of the function at 4 points, okay, x0, x1, x2, x3. How many unknowns are there to be determined? 9. What are they? A1, A2, A3, B1, B2, B3, C1, C2, C3. How many equations are required?
9.
9 equations. Where are the 9 equations? 4.3. Intermediate points. So you can put it as f of x naught. At intermediate points there is only one value of f of x1 regardless of whether you use this polynomial or this polynomial. So for every point you will have two equations coming from the polynomial from behind or polynomial from ahead. How many intermediate points are there if n is the number of intervals? So there are n minus 1 points. So the total number of intervals is 3. So n is 3. Intermediate points n minus 2. So how many n minus 1? N minus 1. So how many equations for intermediate points? How many are there? Every point we have 2. So for n minus 1 points we have 2 into n minus 1, correct? Why every point is 2? F of x1 should be equal to a1 x1 squared plus b1 x1 plus c1 must also be equal to a2 x1 squared plus b2 x1 plus c1. So long as you are applying at x1, whether you use this polynomial or this polynomial, it has only one function. So every intermediate point has 2 equations. So n minus 1 have 2n minus 1. N points, how many equations? 2. Now total is 2n. How many constants are there? 3n. So what about the remaining n? Correct. So there should be continuity of the slope at the intermediate points. Same? Whether we come from left or right. So this f dash of x, that means, what does it mean? 2a1 x plus b1, when you apply it at x1, therefore 2a x1 equal to, correct, good, 2a2 correct, right, like that you can keep on generating. How many such equations you can generate? N minus 1 equations, total number of such equations. So now we have we are still one short. Okay, the slope at the first or last point is 0 or something you are saying. No, you have to start somewhere. Slope at the first point or last point is 0, that means what are you saying? When slope at the first point is 0, what are you saying? A1? What is slope at the first point? D squared f by dx squared. 2ax. Second order, I am talking about f double dash of x. Second derivative, I am sorry, second derivative at 2a1. So when you say the second derivative vanishes at the end point, either a1 is 0 or the a n minus 1 or n whatever is 0. So arbitrarily we put one of these two things 0 if no additional information is required. Is that okay? So last condition, huh? No, but suppose normally we use this cubic spline when there are hundreds of points. When you fit a cubic spline for 100 points, your eyes will not notice that you did some gutbutt somewhere. So make it at the, if you are 100 points, 34th point or 35th point you do, but there is no other way to mathematically close. This is what your graphing software does when you put an approximating polynomial. So much of mathematics goes on in the background. You can write a program in MATLAB and solve it, and then use Excel and put a trend line and this thing approximating polynomial. This is what goes on, right? I can give you exercise, we can have a tutorial class. Suppose I ask you to put a cubic spline with 5 points or something, you will endlessly do that. Yes, Venu.
Derivative condition.
What derivative? You have to give me additional information. Suppose I just have 5 points, data point. Okay, consumption of coffee along with years. X axis years and y axis consumption of coffee. I want a smooth curve. I just don't want a scatter plot. Suppose we give additional physical conditions for some problem, as he says we can use that. But if those physical conditions are not there, we arbitrarily set something. Better to cause the disturbance at the boundaries. So one is linearized. I mean somewhere you have to start, right? So we cannot say it cannot be solved. I mean that's very trivial. So we have to start somewhere. So we will say that we will adjust somewhere and okay. So this brings us to the end of our discussion on exact fit. So there is so much of story to be told about exact fits itself. So these are all properly determined systems where the number of points is equal to the order of the polynomial plus 1 and so on. For example, 3 points we have a second order polynomial, but oftentimes we have overdetermined systems. You do the experiment for finding the heat transfer coefficient for 10 Reynolds numbers. You know that it is a Reynolds number to the power of b into Prandtl number to the power of 1. Okay, if Prandtl number is fixed, right? If you have two constants, two equations are sufficient to get this, but you have 15, you have 10 or 15 data points. So you try to get the best fit. What is your criteria of best? That we have to see. Whether you want to minimize the difference, you want to minimize the difference in a modular form, or you want to minimize the maximum deviation from any point, or you want to minimize the square of the error or higher order power of the error. So we will discuss the general philosophy of minimization, and then we will zero in on the least square minimization, and we will mathematically derive the least square equation, and I will demonstrate to you it is equivalent to getting the maximum likelihood estimate if you have a Gaussian distribution of errors. And then we will do linear regression, multiple linear regression, and we will escalate and end with nonlinear regression using Newton's method.